When I ask people how high they can count on their fingers, I've never had someone not say 10. The answer is 1,023. We've been putting out some videos on how to scale 4 to 20 milliamp signals to some type of engineering units, and it's created a lot of good discussions around precision and resolution. And I realized during those discussions that I need to explain exactly what are these bits, and then we can talk about precision. Because when we think of precision, we think of a base 10 system, whether it be ones place, tens place, hundreds place. In other words, there's some type of precision that way. But we don't actually use a base 10 system when we are looking at analog values. In the end, every processor can either hold a 1 or a 0 in each one of its little bit boxes. Now, I know there's some quantum computing out there that is maybe going to change the world, but it probably won't happen in my lifetime. So as of today, the machines that you see, they're really holding a bunch of ones and zeros in boxes, and that's how they're actually storing numbers. While binary can represent any number, if you have enough bits of resolution, mentally you're going to start struggling to keep track of all those ones and zeros as the numbers get larger. So we started to group the numbers together, and the evolution of our numbering systems stayed in step with the evolution of our microprocessors. And you can Google those because I don't want to get too deep into that. I want to keep track of what we're mentally looking at. So all my fingers down in binary is going to be 0. And then this first one, that's going to be a 1. Now, that's all I can have in this is 0 and 1. So it's the same as a base 10. We're going to go over to the next digit once that one's full. So this is going to be 2, and then 3. Then we're full again, so this is 4, and then 5. We're full again, so 6, and then 7. Now, that's only 7 numbers, a lot of people say, but don't forget about that 0. So we started grouping those together as one number, and we came up with the octal numbering system, which is 0 through 7. Eventually we wanted to do larger numbers than the octal system could do natively, so we added a 4th position. So remember, this was 8, and pretty much every time you add a bit here, you're going to multiply whatever you had by 2. So we're at 8. Now our maximum number is 16. And this is where we get the hexadecimal system. And to represent that, we're going to use our base 10 numbering system, which is 0 through 9. But then we still need 6 more digits for this one. And we're going to use A, B, C, D, E, and F for those. And this is where probably the second most confusing part comes in about numbering systems, is a lot of people think this is 16-bit. No, this is 4-bit. This is the number of fingers that you're counting. That's how many you have. 16 bits means we have 16 ones and zeros there. But so this is 4-bit, capable of 16. 5th bit, capable of 32. 6 is going to be 64. 7 is going to be 128. 8 is going to be 256. 9 is going to be 512. And then 10, which is probably the most confused one, is going to be 1,024. And this is a common analog number, and so people try to equate that 1,024 and 10-bit somehow back to that base 10 numbering system. We never use the base 10, and it comes down to, if you actually look and keep multiplying, I've never even thought about this until this video, none of these numbers ever line up with the base 10 numbering system. So we're at 1,024, then we'd be at 2,048, 4,096, 8,192, 16,384. None of them ever actually line up with that base 10. So while we have to put it somehow back into the base 10 just so mentally we can follow it, it's never actually used. Now, how do I wrap this back around to analog? Because that's where we started here. Those bits represent a certain amount of precision in your analog input. And that's what a lot of you are telling me is, well, I didn't need that much precision, so why do I need to scale it that way? Well, you paid for it. And I've been in applications where the precision did matter. And I'm going to start revisiting my PID series again. And we're going to find out a lot of your PIDs are not working well for this very reason, because you have made your analog signal's too coarse and they're jumping too much from one point to the next point. So next, let's talk about precision as it relates to analog and what it means to have a 10-bit analog signal or a 12-bit or a 14 or a 16-bit. And click here to follow me over there.